All right. Next, we've got Jackson Burns from Massachusetts Institute of Technology. He's working in chemical engineering and computation under the advisement of William Green. His practicum's at Oak Ridge National Laboratory.
Thank you very much. All right, thank you all for being here. Second to last is second to best, I like to think. Today I'm going to be telling you about our efforts into developing deep learning foundation models from classical molecular descriptors. So fair warning, there's chemistry in this talk. I promise not to traumatize you too much, but we are going to learn a little bit, so forgive me. First and foremost, I just want to introduce myself a little bit. There's so many new faces in the room. I haven't got the chance to meet everybody. And I also wanted to make everybody feel old. So I was born in the late 1900s in northern Kentucky. I then proceeded to move to my undergrad at the University of Delaware. This is me when I was a little bit younger and my hair was a little bit longer. But the work that I did there in data science for transition metal catalyzed cross-coupling, actually you'll see sort of echoes of that in the work that I continue to do today, which is my PhD in chemical engineering and computation, specifically on machine learning for property prediction. So machine learning for property prediction in particular, I want to define that. I'm sure we're all familiar with the idea just by different names. And this is the extent of the chemistry, so prepare yourself. For the longest time, if you wanted to try to predict the property of a molecule, what you'd have to do is design some sort of a representation for that chemical. So in this case, this is ibuprofen. If you wanted to predict the solubility, for example, first and foremost, you'd have to really understand what drives solubility. And then you might pick out these, what we call molecular descriptors. So this estimated log P, the molecular weight, so on and so forth. Then you would take some experimental data. You would have your very gifted chemists go and run a ton of experiments. And then you could simply fit it. So you can imagine doing this in an Excel sheet, and you would get a model for solubility. So this is nice in that this is not going to require a ton of data. You have already packed in a ton of human understanding into your chemical representation there. So you're only fitting 5 numbers. But by consequence, if you want this to work on a lot of different systems or on a ton of data, you only have 5 parameters, so you can't do too much. Now, skipping 30 years ahead of time to what we do today and what we do in our group in particular, we have these modern deep learning methods, things like chemprop in particular, which our group develops, that instead learn a representation during training. So if you're like me, you were an experimental chemist for a couple of years or no years at all, and you don't know how to develop an expert designed static representation, you can instead just rely on this algorithm that I'm showing you here. So I won't go through it in great detail, but the short version is you have to choose some features for your bonds and your atoms. These are very basic things like the atomic weight, the order of the bond, things like that, things you can learn in freshman chemistry. And then you do this message passing algorithm, which iteratively updates the representation at each node. Then you just simply aggregate that, and you get this static molecular embedding. So you can think of this as a learned version of these blue numbers up here, and you can just pass that into your regressor of choice. We're lazy, we just use a multi-layer perceptron, and you get your property prediction. So you might be looking at that, and you say, all right, we've got 1 million parameters to play with, we've got a GPU, that's really cool, problem solved. As you might guess from the title of the talk, absolutely not. In practice, these modern methods that I just introduced you to often barely outperform those classical approaches. So the slide that I'm showing you here, this is a linear model trying to predict solubility. It's that same one that I showed you on the previous slide. And then this is our fancy deep learning architecture trained on the latest, greatest NVIDIA GPU. And if you can pick out the metrics there, this one's worse in terms of root mean squared error, mean absolute error, and just narrowly outperforms in terms of Pearson R. So you wasted a lot of compute, and you got something that you can't interpret and doesn't perform as well. Now, this is driven by things that are kind of out of our hands. The data in this field tends to be extremely heterogeneous, very noisy, and in general, there are very few points. So it's not uncommon that a chemist would walk up to you with 200 data points that they had spent literally like 2 years collecting, and they'll say, I'm ready for a machine learning model. We are not in the ImageNet world where we have millions of examples of cats and dogs and things. You have 200 that took, collectively tens of thousands of human hours. So this is the title of the talk. Put into plain English, how can we bridge this gap, unifying the load data requirements of those classical methods with the generality of modern methods? So in one slide, that is the Chameleon foundation model. So if you're one of our users, this is the extent of what Chameleon is to you. You just add from foundation Chameleon, and there you go. You get better results. Talk over. Everybody goes home. But for today, I want to talk a little bit more about the theoretical sort of backing for why we did this and then how we're scaling it now. But behind the scenes, what Chameleon actually does is this is that same schematic I was showing you before. The message passing neural network, instead of being initialized randomly like a normal neural network, we are instead going to initialize using some pre-trained weights. And the novel part, what we have done as part of this study, is come up with a new way to set those weights. So that's shown here. We take our large unlabeled data set just like anybody would, but rather than doing some like self-supervised learning, we're instead going to calculate these what are called molecular descriptors, again from that very first slide. Calculate a giant vector of them, and then we're going to use this masked loss function in coordination with Windsorization, and that, as a pre-training objective, is enough that when you transfer it, you get better results on your fine-tuning. Now, I won't dig deeply into the theoretical part about why this works as much as why we did it in the first place. The devil on your shoulder says that the descriptors that we chose really are not special at all. It's just better than a random initialization, so it's not particularly creative to do this, but it helps. The angel on your shoulder says, nice job. These descriptors are teaching it things like graph navigation, parameterized graph navigation, aggregation, things like that. So there is something more unique to it. But what I really want to talk about, too, is the comparison to the other models. So this schematic you can basically reuse in any foundation model paper from this space and just replace these molecular descriptors that we calculated with any other pre-training target. So some of these other ones that I'm naming here and I have details for on the next slide, they replace those with experimental data, or we've seen a lot of quantum mechanics today. People use QM for both training force fields and pre-training property prediction models. And there are other techniques that use no supervision at all. So particularly using the smile string just as plain text, you can train a text-based transformer model, things like ChemBerta or Moleformer here. So this is the slide that we like to show the chemists because they're always very skeptical of deep learning after having been traumatized by its poor performance for a couple decades. The tagline, Chameleon does in fact deliver practical improvements over baseline models. So the trick for reading these plots, these are Tukey honestly significant difference plots because the machine learning world has recently rediscovered that statistics are a thing. The Chameleon model shown here on the bottom, and if it's in blue, that means it was statistically the best. If it's in gray, that means it was tied with the best model, or at least statistically indistinguishable at our given confidence level. And what I really want to highlight, there are consistent improvements over the baseline ChemProp model. So just by changing your initialization here, we go from the worst model, with the exception of MolCLR, up to the absolute best. Again, same story, among the worst, all the way up to tied with the best. And it outperforms a lot of our other tested methods. So this is just the selection of 6 benchmarks. If we aggregate this across 28 different highly relevant benchmarks for our end users, you can see that we've accelerated ChemProp from only winning on 9 of those all the way up to 21. And then critically, so this RF here, that's random forest, that's similar in nature to the opening linear model that I showed you, just a very strong industrial baseline. So hilariously, we're still barely beating the very, very easy to train, straightforward, CPU-only methods, but we are finally exceeding those. And really what our users tell us, and what we're happy to see, is that this has really changed the deep learning models from sort of an occasionally works well, and you need to try it when things don't go well, to you always will start with a deep learning model as well as these classical methods. All right, and now I've talked exclusively about drug discovery applications, so I would be remiss not to touch on some other topics that are near and dear to my engineering heart. First and foremost is vapor pressure. So this is a particularly difficult property because it's very global. You need to understand the entire chemical nature of the molecule. What I'm showing you here is a comparison against these 2 model architectures from this Kruger et al. Paper. The exact abbreviation is something to the effect of adaptive, graph convolutional, something or another. But what they had to do was come up with these custom designed architectures to fit this data better. So again, in analogy to that opening example I gave you about expert designed representations, we've also just seen expert designed models to try to regress particular properties. And what you're seeing here is the mean absolute error on predicting the log of the vapor pressure. So you can see on this confined data set, which was their smallest one, ironically, we're still not quite approaching the performance of their absolute best one, but when we go to this industry standard Gecko-Q data set, or this broad data set, which covers a lot more chemistry, we are statistically meeting or exceeding the performance of the reference model with the chameleon method, which we're very happy to see, because again, I'm not an expert on vapor pressure. Another interesting one for materials people, or people that really like detergent, surfactant critical micelle concentration is what concentration do you have to mix something until it starts to spontaneously form micelles. If you've ever used detergent, this is what it does in order to get the dirt off your clothes. Again, we were approaching, in this case, a bespoke model called pharmaceutical or farm something hierarchical graph transformer. So you hear transformer there, you think that this takes about a week to train, which it does. Ask me how I know. And again, in this case, we are seeing our chameleon model with no hyperparameter tuning, single shot, approaching the performance of the absolute best model. So they included some other baselines here, graph convolution and graph attention. In terms of R squared, we're like right up there on this data 1 subset. Not quite as good on the data 2 subset. I don't know why they're different, but the authors separated them, again, for chemistry reasons. But what the real takeaway is from this slide is that the foundation models that we're developing are helpful both for the fact that you can regress on small data sets, but also that you can regress on things that you don't really understand the chemistry of, and without having to do hyperparameter tuning or a lot of extensive training. A couple more examples, maybe more relevant to some people here. This is just another very straightforward case where chameleon matches this similarity-based machine learning technique for predicting, in this case, I think it's viscosity for some bio-derived lubricants. On the right here is reproducing the best possible result for predicting some high explosive, so energetic materials properties. I include this one because crystal density is very much a 3D property. You need to understand how the molecule packs together within the crystal in order to successfully predict this. Our model is exclusively 2D, so that was actually a lie. You can get away with just 2D for this property, and with the addition of pre-training, it does really, really well. All right, and then, of course, I need to close the loop on my motivating example. This is the chameleon model on that same data set right from the beginning. So you can see that we have matched the performance in terms of Pearson R on this data set. So this probably means that we've really saturated the benchmark more so than saturated the models in terms of that metric. But the headline that we like is that the root mean squared error is now down to about 1. This is theorized maybe as the limit of accuracy for predicting the log of solubility, about 1 log unit. And the mean absolute error is all the way down to 0.85. So we actually set a new record on this benchmark using our foundation model. And again, trained in 1 shot. All right, this hilarious graphic is a summary of our latest efforts to improve chameleon and get it training at much larger scale. So you might have seen we only pre-trained on 1 million molecules, which is lower than most of the other foundation models. We've recently rewritten the training harness and gotten up to 100 times speed up just using some pretty straightforward tricks in the training world. So the first one was we're now doing shard-wise, semi-random array accesses that are like specific to each GPU. So in the past, this would have been like completely striped together. Each one was randomly getting different rows out of the target array. Now it's all segmented into subgroups. The easiest one, which is literally 1 line in PyTorch Lightning, was just reducing the precision. We realized that we don't know the descriptors down to the accuracy that FP32 can represent, so you can kind of get some free performance just by going to FP16. And then another nice one was changing when we scale our target values from an online scaling done on each batch to sort of an offline pre-training process to avoid those extra calculations. And then this is just a little preview of our new model that we're working on. So we're going to make it a little bit bigger, hopefully. But it's training much faster. The numbers are super tiny there, but you can see that now we could reproduce our model from the first paper in about 20 minutes when it took like 3 days before, which is embarrassing. All right, so with that said, I'm going to wrap up with some acknowledgments. I'd be remiss not to mention David Rogers. He was my practicum advisor when I was at Oak Ridge. He taught me my favorite partial charge scheme and a lot of other really, really useful things that are more serious. I want to particularly thank Akshat for his work on the Chameleon project, as well as my PI, Bill, and then, of course, the CSGF. So the CSGF completely transformed my graduate school experience. Really made it a pleasure to move back and forth between projects and explore what I thought was interesting and could really work. So with that said, I will leave up this paper for the curious. If you want to try this model or you have an idea, please let me know. And follow me on LinkedIn. I would love to see what you all are up to over the next few years after I leave. So with that, I'll take any questions. Thank you.